Hi everyone. Today we'll be taking a look at conditional probability. Okay, so before we get started solving the questions and understanding the concept, let's break this word down. So we have conditional probability. The key term being, conditional in this case. Now, I don't want you guys to memorize what conditional probability is or the formulas that come along with it. Rather, I want to get across the point of get across the idea of how we can solve this intuitively, right? So that's for that. It's really really important that we understand what conditional means. Okay, so looking at the word that as it is in English, right? Conditional means under a condition, right? Under a condition, right? That if A happens, if A happens, right, then B, right? If event A occurs, then only event B can occur, right? The classic example can be, let's say you want a new phone, right? And your parents say, okay, you gotta get certain grades in your school. Okay, so once you can get under the condition that you get the certain grades your parents ask you, they will buy you a new phone, right? That's how it is. If you get a certain number of percentage marks in your test, then you get an A grade or a B grade. That's all under a condition, right? If something happens, if the first thing happens, then the second event can happen as well. That's the whole idea of conditional probability. Okay, now let's take a look at the most basic example. So we have two events here. So event A, or this whole event is of a dice. Okay, it's of a dice. The first event A says the sample space of getting an odd outcome, right? So the odd outcomes are 1, 3, and 5, naturally, right? There's nothing complicated about that. Similarly, for getting a prime outcome, there are three possibilities: 2, 3, and 5, right? And the sample space here is 1, 2, 3, 4, 5, and 6, all the six faces of a dice. Now, let's say that, given the fact that we get a prime number, okay, what is the probability that we also get an odd outcome? Okay, so what I'm asking is, what's the probability that if we get if we get odd number, sorry, prime number, right? Probability of getting a or you know what? Let's make it really simple. Okay, let me just erase this. Let's do one thing. What is the probability of getting an odd number given that it's prime? Okay, probability of getting odd, right? Given that we get a prime number, given that prime, right? So the first condition here in this case is first requirement is to get a prime number, is to get a prime number. Okay, that's the first criteria. After you get a prime number, then we can look for an odd number. Okay, so we know that there are three prime numbers out of the sample space. Okay, out of that, how many are odd? So we have to find, kind of the intersection between these two things. Well, we know 3 and 5 is what is in the prime numbers, and it's odd. So out of the three prime numbers, two of them are odd. So we can say that the probability is 2/3. I hope that makes sense. And again, I'm trying to get an intuitive sense. I don't want to get the formulas in just yet. Obviously, the formulas can make things a lot easier, but I want to show how we can solve this intuitively as well. You can solve these questions with the tree diagrams as well. If your teachers have taught that, that's a great way to solve such probability questions. Okay, now let's get to what the definition of conditional probability is, right? So let event A and B be two events associated with the sample space S. The conditional probability of a given event, of an event given B, where B has already occurred, is denoted as P probability of A given B. Okay, this is how it's commonly written. Okay, so you have your probability parentheses A and like a vertical bar and this, and basically translates to probability of A and B, an intersection of A and B, given that B is already occurring. So basically, out of the probability or the sample size or the probability of event B, you find the common points. Okay? That's why it's conditional probability. Similarly, if you want to go the reverse way, probability of B given A, it's going to be probability of B intersection A, which is the same thing as A intersection B, given probability of A. Right? I hope that makes sense now. It should be super, super easy to work with. Okay? That's the formula. So let's do a let's solve this question that we have. Okay? So we're given that events A and B are such that probability of event A is 1/4. Probability of A, given that B occurs, is half, and the probability of B that occurring that given that A is also occurred is 2/3. Now we have to find probability of B. Okay, so let's break out. Let's use the formula. Okay, so we're told that A given B is the same thing as A intersection B, given probability of B, like this. Okay, so we know this is a half. We have to find this intersection. Okay, and we don't know this. Okay, now let's look at the other formula, probability of B given A. So it's going to be the same thing as A intersection B or B intersection A. It's the same thing. So I'll write it as this and given A. So we know this is 2/3. We know A intersection B. We don't know that yet. So I'll just leave it as it is. And given A is 1/4. Okay. So now I can take this 1/4 on this side. So I'm going to have 1/6. Okay. So this is going to be 1/6 like this. Now I can plug it in for 1/6 here. So I'm going to have, I'll have a half, and then I'll have a sixth probability of B. So probability of B comes out to be 1/3. Okay, so on to the next questions, and we're told that let X and Y be two events such that probability of X is 1/3, probability of X happening given that Y also happens as a half, and probability that Y happens given that X also happens is 2/5. Okay, so let's start by finding the probability of Y. Well, I know I'm given both the conditional probability, so I can definitely find some relation with the intersection, and then I can find probability of Y. So if I have probability of X given Y, that's the same thing as probability of X and Y, and given that probability of Y also happens. Okay, so X given Y is a half. Okay, probability of X and Y happening, I don't have that yet, so let me just keep it as it is, and probability of Y, like this. Okay, so I have some information. I have extracted something out of here. Let's look at the other relation now. So probability of Y given X is X and Y, and probability of X. Okay, so I know this is 2/5. Okay, I can find the intersection probability of both events happening, and I know probability of X is 1/3. So 1/3 will go here, and I'll get X and Y happening together is 2/15. So that's what I have. Now I can put it here and then multiply this by 2. So I get probability of Y is 4/15. Okay, so this is my first answer. That's done. Now we have to find probability of X not happening given that Y happens. Okay, think about it. What does this actually mean? Pause the video and just give it a thought. Okay, so if you've thought about it, this is the same thing as 1 minus probability of X happening given that Y also happens. Right? It's just saying probability of X not happening given that Y happens, and probability of X happening given that Y happens. They're complements of each other. So this is just half. That's it. This is all that it's asking. Okay, now let's solve this question. Let's solve the second part in another manner using a tree diagram. Okay, let's try that. Okay, so let's understand what's happening here with a tree diagram. Okay, so I'm gonna create two different tree diagrams. The first tree diagram, I'm gonna start with X. Okay, and I'm gonna start with X complement, which is 1 minus X, and then I'm gonna have Y, Y dash, and y dash. Okay, similarly I'm gonna have another one here. Okay, it's gonna start with y now, y and y dash, and I'm gonna have x and x dash, x and x dash. Okay, so let's say if I start first with event x, right? Probability of x happening is a third. Probability of x not happening is 2/3. Probability of y happening is 4/15, and probability of y not happening is 11/15. Okay, now what does this second part mean? Now this second part is kind of dependent on x. Okay, so what y is, what this is actually is, it's y given x happening. This is y not happening given that x happens. So if this is y given x, then this is 2/15. I hope that makes sense now. Okay, if this is 2/15, this is 13/15. Got it? I hope that makes a lot more sense now. Okay, now similarly here, we're told that probability of x happening, x happening given that y happens, well, that's a half. Probability of x not happening given that y happens, that's also a half, because it's one minus the other one. That's what we did previously to solve the question. And this part, well, we can figure that out later. But I just want to give a intuitive gist of what's happening. Now, let's say in this situation we found x and y, which was 2/15. So if we want to find x and y happening, which is 2/15, we can just multiply. Let me change this in yellow. We can multiply this and this, right? That's what would give us 2/15, x and y happening, right? And let me just fix this part up. I think I made a mistake here. This should be 3/5. Okay, not the 12/15. It should be 2/5. Okay. Similarly, if you multiply this and this, you'll get probability of x intersection y, right? That makes sense. Got it? And here, if you multiply this, then you get x, x y dash for this one. Okay. So this is the idea of how you can actually solve these questions using a tree diagram as well, because it's conditional probability. It's dependent on whether x is happening or not. It's kind of like that. Okay, so now that you've understood this, let's try this question. Okay, so we're asked that if E dash and F dash are complementary events of E and F respectively, and the probability lies between 0 and 1, then find the value of probability of E given that F happens, and probability of E not happening given that F happens, right? So if you really think about it, probability of E happening given F happens, probability of E dash or E complement or E not happening given that F happens, it's actually just 1, right? It's just 1. Now think about it. Let's say given that F happens, right? So we have F dash, and then we have E and E dash, right? There's some like random probability here. It's 1 minus X, and there's Y. This is going to be 1 minus Y. So they're going to add up to 1 regardless, okay? It's always going to happen that way. Now, if this doesn't really make sense, let's use what we know. We can use normal algebra and arithmetic to solve this as well. Well, we know probability of E given F is just E and F by the probability of F plus probability of E not happening and F happening given by probability of F. Okay, so this is what it is, right? Now, what does this part entail? Okay, so let's say we have a Venn diagram like this. Event E, event F. Okay, like this. Now, probability of E and F would be the middle part right here. But that's not the case. Now we just want probability of E not happening and F happening. That's just this part. This is something, if you didn't know this, if you have seen my previous videos, you'll know that this is exactly what I'm talking about. Okay, so now this can be rewritten as probability of f minus probability of E and F. Okay, so now I have probability of E and F by the probability of F plus probability of F given by probability of F minus probability of E and F. Let me do it like this, by probability of F. This and this part cancels, and I'm left with 1. Okay, that's it. Now, again, let's go back to this tree diagram here that we had, right? So we know there's certain probability of F happening, okay? Let's say it's 50-50, okay? Now, whether E happens or it doesn't happen, the sum of them together is going to be 1. You know, kind of, you know, you can just neglect this part here, and you can just look at, okay, probability of E happening and E not happening together is always going to be 1. It's the same idea, right? Again, this question is, you can solve this algebraically like I just did here, but you can also give it an intuitive reasoning of what's actually happening. And this is something I wanted to share just to get, you know, a concept across. Okay, I want to help build your conceptual strength here. Okay, because that oftentimes helps solve questions, especially those questions which you haven't seen every day, something, you know, that comes out of the box, which requires that out of the box thinking. Okay, so let's look at now multiplication principle of probability. Okay, so what does multiplication principle of probability tell us? Well, that's just a fancy name in my opinion, right? Simply, it's just telling us that probability of A and B is the same thing as probability of A given B times the probability of B. If you notice, I've just, you know, changed the relation. Like, I've just changed the entire equation. Well, normally we had probability of A given B as probability of A and B by the probability of B, right? Because it's a conditional probability. The entire probability is dependent on what the probability of B happening is, right? That's exactly what we did, right? So this is what we're told, and we can use this relation a lot actually to help us solve things. So, and oftentimes what happens is probability of A and B can be written as, you know, B and A as well. So you can bring in the second, you know, conditional probability of A here as probability of B given A, like this, and then you can swap this, you can use this part for here, and you can create multiple relations out of this, you know, all sorts of those things. So again, I just wanted to explicitly state that this, that this solving, you can rearrange the terms in this equation and solve numericals as well. Okay, we'll take a greater look at this in the next video when we look at Bayes' theorem and all those things. For now, yes, I understand, and I'm sure you've noticed this as well, the number of questions we're doing is quite less, because what happens in probability is that we have permutation combinations, we have Bayes' theorem, we have conditional probability, all oftentimes clubbed together, and then a question is asked. So if I start giving in IB style questions or other tricky questions, it's really difficult when you haven't really been exposed to the full picture. Okay, so this was multiplication principle of probability. Now we have what we call independent events. Okay, so in independent events, I think I've already gone over this in the previous videos, where independent events says that, let's say if 2 or more events are happening, right? Events are happening, the occurrence of one doesn't affect the probability of the other event. Okay, let's say there are two friends. Okay, one friend plays tennis. Okay, one friend plays tennis, he's a pro tennis athlete, and one friend plays let's say he plays let's say he's a track and field athlete. Okay, let's say he's a track and field athlete, he runs 100 meter and 200 meter dash. Okay, now if friend A wins his tennis match, what is the probability that, or what's the will friend A winning his tennis match have any effect on his friend B? No. Friend B's performance is independent of friend A's performance, and vice versa, right? They're not going to influence each other's performance. Obviously, at an objective level, yes, that's not going to happen. But obviously, if they're friends, they're going to talk things like that. Oh, you can ignore those things and just understand it at a superficial level at this point. Okay, so that's what independent means. Like even flipping a coin. Let's say you flip a coin 2 times. The what you get, whether you get a heads or tails in the first flip, is not going to influence what you get on your second flip, right? So why am I bringing this up again? Well, for conditional probability, right? Let's say we have probability of A and B. Okay, let's say A is the probability of student A or friend A winning his tennis match, and probability of B is his friend winning, coming first in the 100-meter dash. Okay, so this is just the same thing as probability of A, right? It's the same thing. Or probability of B given that A happens is the same thing as probability of B. Why? Let's break it apart, right? What does this mean? It's the probability of A and B given by probability of B. Well, we know at that point that A and B happening is independent, so I can do this and then divide by B. So this cancels and I'm just left with A. Or you can think about it intuitively, right? What is the probability that A wins his tennis match given that B wins his 100-meter dash? Well, there's no condition on it. A's still gonna win whatever he's gonna win. If A's feeling good, he's trained well, he's not injured, he's gonna win his tennis match. Similarly for B, if B's fit, he's warmed up well, he's in a good mindset. Whether or not A wins, that's not gonna affect B's performance. So that's the same idea here, right? So this is super, super important, right? This is an important relation. Oftentimes we get so bogged up in the formulas that we can neglect this. Again, I'm just trying to give an intuitive feel by giving this situation to you and then giving the formula. Okay, so based off of these independent events, we have a few more relations which can be a little handy. And again, they're pretty simple to understand, right? If A and B are independent events, then A and B not happening, or A not happening and B happening, or A not happening and B not happening are also independent events, right? Think about it. What does this actually mean on a Venn diagram? Okay, so in this situation, right, A and B not happening, right? A and B not happening. That's just this shaded area here, right? That's all that it is. Similarly, what's the second case? A not happening but B happening. Well, that's just A and B like this and like this. That's what it is. This is kind of, A not happening and B not happening. This is kind of like probability of A union B like this. All of it. So this is gonna be like this, A and B, and it's gonna be everything outside, It's gonna be everything outside. Like so. Like this. Okay, these are just simple relations, super intuitive. Once you've got the first idea in the previous slide, this should also make a lot of sense. Again, you can break it apart. This is the same thing as 1 minus probability of B, and then you can expand on this, and then you'll see what exactly is happening. You can break it apart and you can find out. Again, my goal is not to bog down on the formulas. That's something, if your algebra is good, you can always figure that out by deriving relationships. I just want to get the main idea across to you guys. Okay, so now that's there, let me give a little out of the box question here. Again, it's quite common actually. You might find it on the internet, but it's something I wanted to share, and I think it's a good question. So pause, spend some time on it, 10-15 minutes, and play the video once you're done solving it. So in this question, we're told that two children, A and B, are throwing a pair of dice, right? In order to with the challenge that whoever wins throws a doublet. Okay, doublet means either 1-1, 2-2, 3-3. You get the gist of it until 6-6. They continue playing this game indefinitely until someone wins. If A starts the game, then find the respective probabilities of winning. Okay? So let's first do the easiest step. That is, what is the probability of throwing a doublet? Okay? So we know there are 36 possible outcomes, right? Possible outcomes. And out of that, there are 6 outcomes of a doublet. So probability of throwing a doublet, right? Probability of throwing a doublet is 1 by 6. Okay. Now this is the key information here. If A starts the game, okay? So let's say if A were to start the game, then what's the probability that he'll throw a doublet in the first throw? Well, that's just 1 by 6. Okay, that's easy. That's like the easiest situation. In the second situation, A will miss it, and then for A to win again, B will also have to miss it, right? And then A will have to get a doublet like this. And remember, now, do I add them? What do I do? Do I add them? Do I add one, multiply the other? What do I do? Right? That's the confusing part. But remember, let's stick to our basics here. Is A throwing a dice going to affect what B throws? No, it won't. So we know for a fact that they're independent events. Independent events. So usually when they're independent events, we multiply, right? We multiply. So given that probability A misses and B misses, but then A scores, right? That's multiplying, right? Because you have to account for every single possible situation. Okay. Then the third case can be, well, A misses, B misses again, A misses again, B misses again, and then A scores. That's a third possibility, right? That's a third round, technically. There's the first round, second round, and then third round, like this. Okay? I hope that makes sense. So you can kind of see a pattern happening here, right? The only way A can win is if B misses, right? So it's going to be 5-6, 5-6, again and again and again and again, like that, right? That's a situation that's really falling in this case. Another part is that they continue playing indefinitely. Okay, indefinitely. Now, again, let me tell you another, caveat to this question. If you haven't studied sequences and series, solving this question is particularly difficult. Okay, yes, there are multiple ways, but the method I'm solving, or the method that I'm going to be showing to solve this question, will be requiring you to use your geometric sequences and series concepts. Okay, so what you can actually see here in this case is multiple situations, right? So this is, kind of your first term, this is your second term, this is your third term. Now what we're going to do is we're going to have to find the sum of these terms, because you have to account for all of their probabilities, right? This is u1, this is u2, this is u3, kind of like that. And we have to find their sum, because we have to account for all of the possible situations, because it's happening indefinitely, right? It can happen till un. So we have to account for all the possible situations, infinity situations, which can occur for A to win. And these three are situations where A wins, because A is going first. Okay? So now if you remember sum to infinity in geometric sequences, let me change the color actually, because it's all blue. It can get a little hairy now. Let's make it lime. Sum to infinity would be the first term minus divided by 1 minus the common ratio. Well, if you look at this closely, we kind of have a relation happening, right? We can say that un is 1/6 times 25 by 36 raised to the power n minus 1. Well, 25 by 36 is our common ratio, right? This is the relation that I've built now. Again, think about it. How can A win? Right? A can only win if B fails, or A wins in the first shot, which is the easiest situation. In the second round, A can win if A fails, which is 5 by 6, and then B must also fail, right? Because remember, it's either A wins or B wins, right? There's no in between. It's just one winner, okay? Kind of like the mutually exclusive case as well, right? So now this is the first situation. This is the second situation. We have to account for every single possible situation. Let's say this happens 100 times. We have to account for the 100th round as well, which takes place. That's why I'm doing sum to infinity here, not sum to 10 times, not sum to 50 times, right? I'm not doing first 10 rounds, first 50 rounds. I don't care as long as A wins the game, provided that A also starts in this situation, okay? So now that we have established this, now it's just a matter of putting in our numbers. So our first term is 1 by 6 because if we put in 1 for n, we get this to be raised to power 0, which is just 1. So we have 1/6. 1 minus the common ratio, well, that's just 1 minus 25 by 36, which is, I believe, should be 11 by 36. And this comes out to be 6 by 11. So the probability of A winning, given that A starts the game, if A starts the game, is 6 by 11. So what would be the probability of B winning the game? Well, ideally, A if A wins, then B loses, and if A loses, B wins. It's that simple. We don't have to know. It's not A, B, and C playing. It's just there's just one person, right? Either you win or you lose, right? And if one wins, the other loses. Simple as that. So if A wins, right, that's 6 by 11, then B loses. The probability of B losing is 6 by 11. That means if A loses, that's 1 minus 6 by 11, and that's 5 by 11. So probability of B winning is 5/11ths. Now we can figure that out again algebraically here as well. Let's say in the first round, let me change the color. Okay, in the first round, for B to win, A must not roll a doublet, but B must roll a doublet. So that's 1 by 6. Okay, kind of like this, right? Or hold up, so it's 5 by 6, not 5 by 36. I'm so sorry. Okay, right? In the second round, A doesn't roll a doublet, B doesn't roll a doublet, right? Then we have A again doesn't roll a doublet, but B rolls a doublet, like this. Okay, so our first term is 5 by 36 now, and our common ratio becomes again 25 by 36 times 5 by 36, and I can do this raised to the power n minus 1, like this. Similarly, third, I'll just show it for the sake of showing it. I don't really need to, but again, both fail second time, and A fails the third time, but B makes it. Sorry, ignore this. Like this. So this is 5 by 36 times 25 by 36 raised to the power 2. Again, n minus 1, so 3 minus 1 is going to be 2. So now again, I can do sum to infinity. My first term will be 5 by 36, 1 minus the common ratio, which is 25 by 36. This should give me 5 by 36 by 11 by 36. 36 cancels out. I'm left with 5 by 11. So this is the probability of B winning if B goes second. Again, if B were to go first, it would be 6 by 11. That's the only difference here. So if you're ever flipping or rolling a doublet with your friends and you want to figure out, who has a higher probability of winning, the person rolling, first has a slightly higher edge, I would say, roughly by 9%. It's a minimal difference, but yeah, it's there. If you're gonna bet who's gonna win, chances of your friend throwing the dice first, whoever throws it first, is much higher. Okay, so yeah, this question can kind of be extrapolated to 3 children throwing a pair of dice, and kind of doing that can get much hairier. But I just wanted to show again how probability is incorporating another concept of sequences and series, which was one of the first playlists I made it. And you're using that concept also to solve probability questions. Now you can combine this with permutation combinations, and you can have 100,000 possibilities, millions of possibilities of questions that can actually arise from this situation. Okay, so with this, I'm going to wind up conditional probability and multiplication theorem. Going forward, we'll look at Bayes' theorem as well, which is which is highly, not highly, very much the same as what conditional probability deals with. It's just a theorem, so I think it's important to get that across as well, because it's the, the benchmark, or the founder, the cornerstone of what probability also talks about. Okay, so this was all for today's video, and I'll be seeing you in the next one.